Over the past century, the semiconductor industry has shaped the world like nothing else. Semiconductors are now omnipresent, powering technologies from cell phones to the Mars Curiosity to the Mars rovers like Curiosity, Perseverance, and Economy. And in 2021, the worldwide semiconductor sales totaled an amount which is pretty big, which is half billion, and exactly it's 556 billion US dollar. Semiconductor design, which includes the design of both physical integrated circuits and the associated software, accounts for roughly half of all industry R&D investment and value add. So value add is the amount by which the value of an article increases at, at each stage of its production. So semiconductors are critical to the functioning of the modern world, driving economic competitiveness, national security, and technologies ranging from modern defense capabilities to autonomous vehicles. The semiconductor industry is of high strategic importance, and semiconductor manufacturing is increasingly the focus of industrial policies across major economies. So, where and how did all start? What is the genesis of semiconductor industry? So, to know that, we have to rewind a bit, look little backward, and it would enthrall us to know that the semiconductor industry has an India connection also at its root. And would you believe if I say that Swami Vivekananda too had a role to play in it? I think it's a little, you know, counterintuitive, but that's a fact, right? So the semiconductor industry has an India connection. So let's look back and figure it out. You can go to the next slide. So more than 150 years back, the German physicist Ferdinand Braun made an interesting discovery in 1874. He observed that pointed ends of thin metal wires in contact with sulfides like galena behave peculiarly when current flows through the metal and sulfide junctions. The resistance of the junctions diminished significantly when the electromotive forces were applied across them. To his surprise, Braun realized that the setup departs from the traditional Ohm's law. So you have to remember, right? It's 150 years back when semiconductor was not even known to anybody. People only knew about conductors, and Ohm's law was the only thing that they knew, that the current and the voltage is proportional. But Braun figured out that the current flowing through this uh, junction, which is the galena and the metal junction, is not following Ohm's law. What Braun discovered was not something ordinary. It was the first metal semiconductor junction diode. The galena crystal being a semiconductor, a transient substance between the conducting metals and the non-conducting insulators. But however, this came to be known only many years later, because in 1874 nobody knew about semiconductor. The term semiconductor itself was not even coined. Forget about understanding the functioning of semiconductor, which needed quantum physics, and all those things came much later. Even Einstein came up with his special theory of relativity in 1905, followed by the general theory of relativity in 1915, and quantum mechanics, quantum physics was at its infancy in the first 2 decades of the previous century. And the functioning of semiconductor is impossible to impossible to understand without the knowledge of quantum physics. So what Braun discovered in 1874 was just an observation. Nobody knew what was that. 2 decades later, in 1890s, an Indian scientist, Jagadish Chandra Bose, working alone at his small laboratory in Presidency College in Calcutta, came across Braun's discovery. He replaced bronze metal wires with an iron whisker and made it touch the galena crystal, thus creating his galena detector, which, to his surprise, detected visible light too, besides the invisible electric waves or the radio waves. driven by Jagadish Bose's urge to use Indian names rather than Latin or Greek, as was the norm of the day. He called he called this universal detector. I mean, he called it universal because it detected both light and radio waves. At that time, it was already known that light and radio waves both were electromagnetic waves, and so he called this universal detector and he named it tejometer. Sanskrit tejas means light, fire. It also means splendor and brilliance. So very poetically, he named the universal detector that he created as tejometer. Unknown to him at the time, Bose's tejometer was the world's first semiconductor device put to practical use. Soon, he filed a patent on it in the US with one Mrs. Sarah Chapman Bull as his co-inventor. Soon, when the patent was granted in 1904, it became the world's first patent on a semiconductor device, a diode, to be more precise. Bose used this galena diode or the first semiconductor diode to detect radio waves a few millimeters in length. So he used this to detect millimeter waves, to be more precise. Now, deviating from the Ohm's law, the current through the diode was not linearly proportional to the voltage or the electromagnetic force applied across it. Moreover, unlike a conductor which conducts the same amount of current in either direction, the diode conducted different currents in two different directions. I think now you know very well, right? Diode uh, acts like a valve. So, Bose Galena diode was also one of the simplest logic gates. It it acted as a crude rectifier or one-way valve. It gated or obstructed the current flow in one direction, right? So that's the most simplified logic that you get. I mean, much before the AND gate or the OR gate, right? You had this rectifier, which is also a gate, right? It obstructs or gets the negative current, or in the parlance of AC and DC, if you pass an alternating current through a diode, it transfers only the positive signal, and the negative current is blocked. So that's what we call a rectifier, right? So that was what Jagadish Bose discovered or invented without knowing what it was. More than 100 years later, IEEE inducted Bose's achievement in the list of IEEE milestones. A plaque with the citation First Millimeter Wave Communication Experiments by J.C. Bose 1894-96 was displayed in the main corridor of the A.J.C. Bose Auditorium in the main building of Presidency College in Calcutta in the September 2012, a little more than 10 years back. They also added, meaning IEEE added in the notification that it was the first millimeter wave communication system in the world. So wireless communication with millimeter wave is again a fad now with the advent of 5G, more than a century after process experiments involving semiconductors and wireless. The two technologies that have touched humanity in ways more profound than anything else in the last 100 years. So now you would be curious to know who Bose's co-patentee Mrs. Sarah Chapman Boole was. Yes, so that's where the things become very interesting. She was a disciple of Swami Vivekananda who traveled to India in the late 1890s to serve India, to serve her master Vivekananda. In an act of serendipity, she became a motherly figure to Bose. And it was under her pursuance that Bose finally filed a patent that heralded a new age, which we call the semiconductor age. So that's what, I mean, the genesis of the semiconductor age has a very strong India connection. I think we all should be very proud about that. So we can go to the next slide. Can we change the slide, please? Yes. Now that we know where from it all started, let us see what happened next. This one, what you see in the screen, is a pamphlet I have taken from Motorola Freescale. uh, one of the earliest semiconductor companies. A lot of you might not have heard the name of Freescale. They are part of NXP now, but like Motorola was one of the earliest semiconductor companies in the world. So this chart, uh, which was published in the early 2000s, right? It was celebrating their 50 years of functioning, their 50 years of semiconductor production. So, so this also gives a very good idea or a very good picture about what exactly happened over the last 70 years. Starting from the 3 amp power transistor in the 50s, we have come a long way to today's GPUs that are behind all the hoopla about AI. In the 60s, Motorola came up with their first silicon-based transistor. The 16-bit processor MC68000 came in the 70s. 32-bit processor MC68020 came in the 80s. The first surface micro-machined inertial sensors for automotive airbags came in the late 80s, initiating the use of electronics in cars. The PowerPC, a RISC is reduced information set computer, a RISC architecture-based computer created by the 1991 Apple IBM Motorola alliance, which they called AIM alliance. So this PowerPC, created by this AIM alliance, came in the 90s, introducing us to the world of PCs. The first communications processor came in the late 90s. The first single core modem, which Motorola called smartphone on a postage stamp, came in 2003. And then the IMX31 processor for mobile multimedia entertainment came in 2005, ushering in the new millennium. And ever since that, mobile has become a very important part of our life. Like this multimedia entertainment processor which came in 2005, that was a milestone thing because now we cannot think about multimedia without mobiles. So this takes us through roughly about the evolution of the semiconductor industry. We can go to the next slide. And now, as a report by the Boston Consultancy Group and Semiconductor Industry Association have put it across aptly, they are saying semiconductors, I'm just quoting from their report, semiconductors help automobiles generate safety. Uh, automobiles operate safely, advanced medical equipment save lives, and military radar systems detect dangers. So very subtly, the report has highlighted the shifting trend and dynamics in the semiconductor industry. It's no longer the world of electronics, the mobiles, computers, and servers that need the semiconductor chips to thrive, but it's the very safety, security, and the health of the nations that hinge on the humble and benign silicon that comes from sand. The next war could very well be the chip war. In fact, there is a very popular book called Chip War, which talks about the importance of the semiconductor industry and how it has become very important to all the countries. So he is calling it chip war, and a lot of people say are of the opinion that the next world war, if it happens, right, that might be the chip war because any country which has uh, you know like the edge over semiconductor industry, any country that can manufacture more chips are would be more powerful. So no wonder that suddenly all countries have realized the power of sand, which is silicon. You can go to the next slide. Yes. So now that we have talked a little bit about the history of semiconductor industry, now let's see the changing landscape of the industry leaders. In the 90s, as you can see, the champ was doubtless Japan, propelled by companies like NEC, Toshiba, Hitachi. I can see the name of Fujitsu, Mitsubishi, Matsushita. Um, and holding the fort for the Americans were Intel, Motorola, and Texas Instruments. Only three companies. and the majority of the companies of the leaders were from Japan. Now, in the next decade, which is the 2000s, few of the top Japanese players were kicked out by the newbies like Samsung, ST Micro, Infineon, and the old timer Philips, introducing Korea and Europe in the game. So now we have Japan, US, Korea, and also Europe. Japan slipped further in the next decade as the American hegemony picked up with the entry of companies like Micron and Qualcomm in the top 10. And now in the 2020s, 7 out of the top 10 are American companies. But that doesn't mean that the next decade, which is the 2030s, the leader will be America, because if you see every decade, the leadership is changing. So you never know which country will be the leader in 2030s. Uh, it could be India also. You never know with so much focus going into semiconductor. But again, nobody knows that. We still have 6, 7 years to come to the end of this decade and the beginning of the next decade. Let's go to the next slide. So presently the top 10 semicon E-R&D spend. So E-R&D is engineering R&D. So presently the top 10 semicon E-R&D spends accounting for close to 76 billion US dollar, or roughly a third of the total spend, come from companies like Apple, Samsung, Intel, Qualcomm, Cisco, Nvidia, Google, and others. Next, accounting for nearly a fifth of the total spend are 15 companies, which include European automobile giants like Volkswagen, Daimler. Daimler is the one which makes Mercedes Benz. Apart from companies like Microsoft, Micron, MediaTek, and Broadcom. The next 25 companies, which is 26 to 50 in the chart, making up to 1/8 of the semicon ER&D spend, are automakers like Ford and BMW, aerospace major like Airbus, diversified biomedical equipment manufacturers like Siemens, Philips, and Johnson & Johnson, and others like I guess Applied Materials, Texas Instruments, and Renesas. Notably, Gamma, which is the acronym for these five companies, Google, Amazon, Meta, Microsoft, and Apple, alone contribute to more than 25% of the top 25 semicon ER&D spend, amounting to $31 billion. So the market landscape makes it very clear that the companies to watch out for are automobile, aerospace, biomedical, and gamma, which would drive the semicon spend in future, not the conventional mobile and compute companies. I think this is a very, very important trend which is happening, and I believe when you will be starting to work, right, your focus will no longer be the mobiles or the computers. Though the semiconductor started mainly for mobiles and computers, but if you see the trend, the the companies which will be the bigger users of semiconductor chips would be automobile, aerospace, biomedical, and of course gamma, which is the acronym for five big behemoths: Google, Amazon, Meta, Microsoft, and Apple. You can go to the next slide. Next, let us look into the different types of semiconductor chips that are produced and who's making the most. So if you see here, the US is the long-standing leader in semiconductor design, accounting for more than 60% market share in microprocessor, controllers, and other technologies that enable the execution of computing operations, and that which are built with logic gates. So the first, the first line, if you see in the chart, which is called logic, they constitute all these things, the microprocessor, microcontrollers, everything. And again, the logic, when you talk about logic gates, I think you would remember I just talked about something that the most simple logic gate was produced or invented by an Indian, Sir Jagadish Chandra Bose, more than 125 years ago. US also designs a fourth of the memories, close to 40% of all the DAOs. So DAOs stand for discrete analog optoelectronics sensors and others. So, when we talk about semiconductors, we often forget that sensors are also a big part of the semiconductor. Sensors are everywhere, right? We don't see them, but there is no electronics without any sensor. So they also constitute a very important segment. And overall, almost half of all types of chips in the world is also produced by US. So this is the, if you see the design subtotal, right? If you see almost 46%, which is close to half of all types of chips in the world are still manufactured. Okay, not manufactured but designed by the US. Let's go to the next slide. So now, like, who are consuming all these chips? So almost a third of all these chips, which we have talked about in the previous slide, are now being consumed each, in computers and communications. So one third, around 33% each in sort of computers and communications, a little more than 10% each in consumer, industrial, and automotive electronics. So this is where all the chips are going. Let's go to the next slide. Can we go to the next slide, please? Okay, so uh, if you, when from the previous slide, though automobiles are now using a little more than a tenth of the total semiconductor produced, or the a tenth of all the semiconductor chips that are being produced, their consumption is expected to grow at a CAGR of 13% in the current decade, which is more than double the rate at which the same is slated to grow for computers and communications. So by 2030, automobiles can very well consume a fifth of all the semiconductor chips produced in the world. And, at, and in 2030, computers and communications might use a little more, around 25% each. So if you see, in 2030, automobile, computers, and mobiles, all of these three might be using similar number of chips, like similar proportion of the chips produced in the world. So that shows where the trend is going, right? So very soon, like, your car will be more electronic than anything else in the world. We can go to the next slide. So now that we're talking about, so many electronics being used by cars, so let's see, what are the chips that cars consume. So there could be up to 100 microcontrollers for powertrain, chassis and safety, infotainment, ADAS, etc. in a car. Almost 100 analog chips for power management, RF, radar, and drivers for motor, display, and LEDs, and up to 130 magnetic sensors for current, position, and speed sensing. So this gives you an idea of why the cars would be, eating up so many chips in future. Let's go to the next slide. The next slide, please. Yes. Okay. So now that we have learned a bit about the genesis of the chips, who make them, and in how many numbers, and where they go into, now I think it's time to know a little bit about the various stages involved in the designing of these chips. So the chip design process starts with something which we call product definition and specification, during which the market data and the customer inputs are analyzed before finalizing the system architecture. So if I have to give an analogy, this is, you can say, similar to the mayor, like similar to the mayor of a city deciding upon constructing a new township in the outskirts of the city to decongest the downtown, right? So, like, that's what we call the product definition and specification, right? So we have to take inputs from the market, like, say, in the example of the mayor, right? The mayor might be getting inputs from everybody that the downtown of the city is getting congested, so we have to shift people to a different place. So a new township has to be created in the outskirts of the city, right? So these are all product definitions, right? And also you have to come up with the, I mean, the definition, and more than definition, also the specifications, right? So that is the initial stage. And then the second stage, in the second stage, the system architects define the block level architecture for the design, which is analogous to architects getting down to the nitty-gritty of the different parts of the township, like the children play area, the shopping areas, the apartments, etc. This stage is followed by designing and verifying the integrated circuits, which is not much different from the structural engineers, drawing up uh, the detailed plan about the beams and the columns, the masons building the structure brick by brick, and the engineers carrying out their timely inspections and the checks to ensure that the construction is progressing as per the safety and the other norms, right? So this is the third stage, which is the designing of the integrated circuit and the verification. So then the final stage and the last stage, when the chips have been fabricated and it's the post silicon phase, they must be tested. So which is again similar to how experts survey a construction site before giving clearance certificate for occupation. So these are the four main stages of a chip design. We can go to the next slide. So designing of a chip is not a cheap affair. It's a very costly affair. You can see from the chart, a 5 nanometer chip can cost up to half a billion US dollar to design. So that is how costly the chip design is. Now let's go to the next slide, which will talk about the chip designers. So one third of the world's chip designers are in the US, comprising almost half of the world's semiconductor revenue. But unfortunately, though India has close to a fifth of world semiconductor, world's chip design population, we don't yet have a single penny in semiconductor revenue. So that's very ironic, and it's very sad that an Indian scientist holds the patent for the first semiconductor device, and at present the semiconductor revenue of our country is zero. We don't manufacture a single semiconductor device in our country, but there's a good news that things are changing soon. So the next few slides will uh, talk about that. What is the prospect of India? So let's go to the next slide. So I took this picture in the Semicon India 23 summit, which happened in Gandhinagar. I believe it happened in the month of July. So if you can, see the people who are sitting in the dais. So this entire thing, I just took a picture from the dais. So it had a big screen on the top where it says that where the Prime Minister Narendra Modi was there on the dais, and he pledged financial support worth 76,000 crore rupees, which is close to $10 billion towards manufacturing semiconductors in India. And if you see the people sitting from the left, the first one, if you can see, he's the CEO of AMD, I think Mark Peppermark. To his right is Anil Agarwal, who is the chairman of Vedanta Group. To his right is the CEO of Foxconn. I cannot remember the name. And to his right is Rajiv Chandrasekhar. He is the Minister of State in charge of electronics and IT. And then to his right is the Chief Minister of Gujarat. And to his right, I believe everybody can identify our Prime Minister Narendra Modi. To his right is Ashwini Vaishnav, who is the current cabinet minister for MeitY, which is in a short form for the Ministry of Electronics and IT. To his right is the CEO of Cadence, Anirudh Devgan, and to his right is the CEO of Micron, Sanjay Mehrotra. So all the who's of the industry were there in the dais, and in front of everybody, Narendra Modi made this pledge that India will spend up to 10 billion US dollar uh, towards manufacturing of semiconductors. We can go to the next slide. Okay, so the next slide says that India's semiconductor market may reach $110 billion in the present decade, accounting for 11% of the global market. So we are at zero now, and that is what our Prime Minister Narendra Modi wants to achieve in the next 7 years. From zero, we want to go to $110 billion in the manufacturing of semiconductor, which will account for 11% of the total semiconductor produced in the world. Let's go to the next slide. I think that is the last slide. So now, which all areas will India focus? So these are the things which were pointed out: semiconductor fabs, and you would have already learned that India is very optimistic about setting up the fab in India. And then apart from the semiconductor fab, display fabs, compound semiconductors, packaging and testing, and other fabs. Right, these are the few areas where most of the investment and most of the activities will happen in India for the in the coming years. So I think that's all. I mean, that is what I have, and I think now we can open it up for some question and answer. I believe we still have 10-15 minutes. So I would like to interact with you if any one of you um, have have any query or anything that you'd like to ask me. I would be more than happy. So okay, so I don't know how you would like to do. You would like to. I think somebody can I mean go through the chats like Gaganshri. I mean, if you can take the responsibility of
Yes,
reading out. I mean, whatever they write in the chat, then I can talk about it, because if everybody starts talking, that might be a little bit of problem. So why don't everybody of you who wants to ask question, right? You type your question in the chat box, and Gaganshri, you can moderate that, and you can just read it out, and I will try to answer one by one.
sure, sir.
Yeah.
Vedant and Shubhankar, you guys have raised your hands. Can you
Yes.
just put the question on the chat?
And others who want to also ask, why don't you just write? I mean, start typing in the chat box so that we don't waste any time, right? So Gaganshri can read out the chats one by one. Yes. Do we have it?
Yes, sir. There's one question by Shreyas.
Yes.
What are some industry skills one must have to enter this sector, both from R&D and manufacturing?
Okay. So, I mean, for manufacturing, I believe we still don't know. I mean, what type of skills should be needed, because we haven't, the fabs and all those things haven't yet started, right? But uh, most of the jobs in the fabs or in the manufacturing side would be on the material science, I believe, and also a lot of technicians jobs, right? So, um, I mean, engineers might not be needed for the manufacturing and all those things, right? I mean, because they are more on the factory, they're more of factories, right? But still, I understand, people with material science knowledge, and also mechanical engineering, chemical, electrical, all this core engineering, people would be needed. But for the R&D, yes, for the R&D, I think core VLSI, knowledge will be needed, right? I mean, whether it's I mean, I talked about the four phases, right? Uh, the first phase is actually design, definition, definition and like I mean, system specification. That I think generally to enter the industry, right? That is something that you might not get an opportunity to do because generally, the definition and the specification, the system level specifications and all those things are defined by the senior people, right? And the second one, which is again, I believe, which we are calling, you know, I mean, uh, like the first one is a product definition, and the second one is, I mean, specification about the various blocks, right? That is also something that directly fresh from the college you might not be doing. Bulk of the activities that you'll be doing is in the third stage, right? Which is the designing and verifying the integrated circuits, right? So that's where you need this RTL design, you need physical design, you need DFT, you need I mean RTL verification, right? So the third stage is something that most of the companies hire a lot of fresh people from college, right? Because that's where the main bulk of the work is, right? So I believe, I mean, most of the colleges nowadays have VLSI courses, right? So I think, basic, I mean, whatever course you have in VLSI, that should be more than enough. And whichever company you join in the R&D space, they would be having their own, training, right? So there is no, I would say, specific skill needed for this thing, right? For at least for the, uh, I mean, the R&D part of the VLSI or the semiconductor design, but if you are going to embedded software or AI, so that has not much to do with VLSI, right? I mean, that is pure computer science related background and pure software background, right? Yes, can we go to the next question, please? Gagan, see if you can
Yes, sir. Yes, sir.
read it out.
Yes, sure, sir. Can you shed some light on how the classification of consumer, industrial, military, and aerospace grade semiconductors electronics takes place? That's one part. I know
Okay.
temperature is a factor, but anything else? And how does this affect manufacturing and supply?
Okay, can you read it once more?
Yes, sir.
I want to just make sure that I got it correctly. Yes,
Yes,
please.
sir.
Can you read it once more, please?
Can you shed some light on how the
Hmm.
classification of consumer, industrial, military, and aerospace grade semiconductors electronics
Oh, okay,
takes
okay, got it.
place?
Okay. Hmm. Okay.
I know temperature is one factor. I mean, this is
Hmm.
the co-synthesis part I think they're talking about.
Okay.
And how does the this affect manufacturing and supply?
Okay, got it. Got it. Okay, so again, different industry has different criteria, right? Like for defense, right? For defense or for medical, right? The reliability is the most important thing. The size or the speed or I mean, low power or uh, all these things are not very important for defense or medical industry, right? And in general, automobile, defense, and medical industry, right? They still use pretty old technologies, right? Which are sort of 20, 30-year old. Because what is more important is the reliability, not the power or area or speed. Like in the mobile, what is more important is what we call PPA, power, performance, and area. Right? A mobile has to be as powerful as possible, and it should, it should take as less power as possible. It should be as fast as possible, and it should be as small as possible. Right? So that's why all the latest, I mean, technologies go into mobile. But if your mobile fails, right, you don't lose life. If your mobile fails, like if your mobile doesn't function, you might be very unhappy. You might, write a bad review about that phone company in Google or whatever, but you are not losing your life. Correct. So the newest technologies are always tested on things like, consumer electronics or mobile computers where there is no threat on life. But when it comes to defense and automobile and aerospace and biomedicals, right? There, the most important is the reliability and that's the reason they still use sort of 20, 30-year old technologies, and they don't care about power. Like an X-ray machine can eat up as much as as much power as possible, and nobody complains, right? You don't want to carry an X-ray machine in your hand, and then you don't want to put an X-ray machine in pocket, right? So the gradation of the electronic devices, or the gradation of the chips, are again done on this basis, right? I mean, if the reliability is a factor, then again which technology node you use, and then the longevity, right? I mean, when you buy a car, I mean, as I mentioned, right? I mean, you would have seen that the automobile sector would be using close to 20% of all the chips manufactured in the world. So these chips have to be extremely reliable, and it should have an extreme long life, right? Meaning, suddenly after 10 years, if the chips start malfunctioning, right, it will be disaster, right? But a mobile phone you never use for so long. So longevity, reliability, all this thing comes from from the technology, and also the process you have been following. More and more a process matures, more and more that process becomes suitable for all this automobile, aerospace, and defense, and biomedical. And now for the temperature, I believe somebody asked what is the impact of temperature. Again, I believe a mobile phone, you will never take it to a place where the temperature is more than 50 degree, right? I mean, no place in the earth exists where temperature is much more than 50 degree, because humans will never go, right? So generally a mobile phone, or most of the consumer electronics things, are needed to operate in temperatures where human can also live, can also sustain. But when it comes to defense, right, or aerospace, right, when a chip goes to moon, I think recently you would have seen during the Chandrayaan 3 rover landing, right? I mean, you would have read in newspapers that the rover that was uh, the Pragyan, was it called Vikram or Pragyan? I think Vikram was the lander, and I believe Pragyan was the rover, which is still moving on the moon surface, right? So they didn't know whether the rover will still operate during after after crossing one lunar night, right? Because they landed at the beginning of a lunar day, and then it operated for one full lunar day. But the moment it went to night, our scientists were not very sure whether the rover will still function when the next day comes, because during the night the temperature goes very low in the lunar south pole, right? The temperature could have gone to some minus 200 degrees Celsius, right? So nobody knows whether a chip will operate at that temperature, right? So that is the level of reliability which is needed for aerospace, or space programs, or even in industrial automation, right? I mean, a lot of chips are used in furnaces, right, and other places, right? I mean, where temperature can be very high. So temperature plays a very, very big role in all these areas: defense, aerospace, biomedical, not that much, and especially in space programs. But in consumer electronics, right, you don't care, right? Because you don't need to deal with temperature which human beings cannot sustain, right? Human beings can sustain, I mean, in how much? Minus 50 to plus 50, right? That's all you need. So I think that might have answered your question, right? The gradation of the electronic product, and also the dependence on temperature. Yes, can we go to the? If we have some more time, we can go through a few more questions.
Yes, sir, there were few more questions.
Uh,
So this is by Vedant, and he asked, as you said that the economic revenue that can be generated in India in the semiconductor
mm,
industry is expected to be
mhm.
110 billion. But
Yes.
how would you counter or reduce the cost relating to procurement of raw materials, labor cost, etc.?
Okay. The good part is that raw material is silicon sand, right? So that is the good part about the semiconductor, right? Silicon is the most used semiconductor, and silicon comes from sand. But then, if it is galena and all the other things, right? I mean, there are other, semiconductor, material, right, which are also used, but still now, and also in the next few decades, silicon would be the main semiconductor material. So that is not the problem. The few things are important. One is pure water and uninterrupted uh, power supply, and thirdly is extremely clean environment, right? So I believe none of this is dependent on external sources, right? Because uh, I mean getting uninterrupted power, that is, again, I think we have enough technology in India to and also enough I think know-how to have uninterrupted power. Gujarat already has like Ahmedabad. I remember. They don't have any UPS, right? The all the computers and everything are directly connected to the power point, meaning to the electric supply, right? So I believe uninterrupted power supply shouldn't be an issue. What is important is the ultra clean. Spaces and extremely pure water supply, right? So again, they don't need much of external imports, right? We don't have to import anything much for that. What is important and what is I think the most import heavy thing are the equipments, right? Because none of the these fabs, right? Most of the equipments that we use, the etching machines and everything, they are mainly manufactured by one or two companies in the world, and one Dutch company supplies, I think, almost 100% of of these machines, which which companies like TSMC or other fabs buy. So yes, we need to import a lot of things, but I believe it's more about setting up the process, and also inculcating the skill. You have to develop the right set of skills needed to run the fabs, right? See, the on the R&D side, we already have enough knowledge, because, as I told, right, one-fifth of the semiconductor chip design engineers reside in India, and so it is not a joke, right? India has one-fifth of the designers, so that itself gives enough muscle power for the chip design industry. But what we don't have is the skills and the knowledge needed to run the fabs, right? Again, those are, as I mentioned, those are not pure VLSI or semiconductor related knowledge. They are mainly material science, mechanical, electrical. So all the core engineering knowledge is also needed, right? So I believe, yes, we are in a pretty good I believe state. And most important, right, more than anything else, is I think the urge. If we really want to do, meaning the government has to support and the entire ecosystem has to support. Only government single-handedly cannot do, and only private companies single-handedly cannot do. Right? It has to be done in a very like collaborative manner. And what is most important is the urge, and is the this intention to do what a TSMC did 30, 40 years back, or what Taiwan was able to do. Well, it can be a role model, right? Where government came forward and pledged a lot of money, because these fabs and all these things are extremely costly, right? And as I have shared, some of the pictures from the Semicon India 2023 summit, right? Uh, our Prime Minister himself is pledging close to 10 billion, which is, of course, not a very big amount when it comes to fab, but to start with, that's a pretty good amount, right? So yes, we have the intention, we have the designers. You are the future designers, and and also, like, many of you would be going to the manufacturing side also. So I believe we have everything needed, from intent, interest, from ideology, from and also from talent. I think we have everything. So I am really optimistic. And yes, I might not be working over the next decade, but you all would be are working for the next 3-4 decades, right? So you will be part of this big movement that India will see, which is the semiconductor movement, if I may call it, right, or the semiconductor manufacturing movement, right. You all would be part of that. So I think you are at the right time at the right place. And you will do wonders, and I think the country would be depending on you for everything that she does in this domain. Any other question?
Yes, sir. One last
Yes,
question.
please.
Seeing the it's by Akshat. Seeing the current trend of developing more and more efficient process nodes,
Okay.
how do the old, better yielding giving process nodes stand in current market? What should be India's main focus? More advanced semiconductors or bulk old semiconductors?
So is it related to? I believe it is related to India. Okay,
Yes, sir.
I'm really impressed that. Raganshri, would you please talk about the profile of the people who are in this like call? Are they BTech
Yes,
students
sir.
or
All
they are
are
from
BTech,
MTech? All are
all
BTech?
are
Oh
BTech
wow!
undergraduates.
Oh, so that's very interesting, right? I mean, when I was a BTech student, I did my BTech from IIT Kharagpur. I mean, I don't think I could have asked any of these questions, right? I mean, first of all, I didn't. I mean, in those days, right? I mean, I did in '96, and we didn't know about any of the things that you are even asking, right? So I am I am extremely happy that when you are asking all these questions, and I'm suffering from some inferiority complex about myself. That I mean, I might have been not even like 1/10 smart as you all are. So this, I mean, this is a very nice questions, and even I mean, we also ask all these questions in interviews for for senior hiring, right? In like, and you, when being in final year, I believe you're asking all these questions. I mean, first of all the best. So I, to paraphrase the question, you are asking about what should India focus on, the
Right.
low, the old high yield, high yield and highly, I would say, I mean, highly reliable processes, or the new age thing. Okay. So what I understand that India would be investing on the older technologies, right? For many reasons, right? First of all, yes, older technologies have better yield, and when we are starting, right, we cannot have a technology where the yield is low, right? So it makes more business sense to invest in a technology which is old, which is reliable, and which is also cheap, right? Because like say 130, like 0.13, or which is sorry, I mean 130 130 nanometer, right? So when I started working in the 90s, at that time we had all this 130 nanometer, and then 90 nanometer, 65 nanometer came in the around, I think, 2003 or 4, we had 65 nanometer, right? So 130 nanometer and 280 nanometer, right? So which is 0.28 micron. These are extremely, I mean, reliable things. But what I understand, that I believe we might, the first fab that India might have would be 40 nanometer, which is close to 20-year old. The yield is high, reliability is also pretty high, and I think a lot of equipments that a lot of chips that can be manufactured can be directly consumed in India, right? And lot of chips which are needed in India for for the basic consumption can be produced in India. Like say, the chips needed for automotive car is not something that India needs, right? I mean, why would India need I mean, automotive car even after 30 years or 40 years? Also, like India, the most needed thing in India might never be automotive car, right? I mean, so if we don't produce chips for automotive car, I think it's fine, right? What India needs most are mainly, a lot of chips that would, I mean, that would go for agricultural industry, right? I mean, that will help in industrial automation, that will help in a lot of IoT based products, which will improve the yield of agriculture, which will improve the like which will improve healthcare, right? Education, right? So some of the major things which India needs and which India cannot get rid of, unlike other countries, like USA is not an agro-based country, right? USA is not a country which has to invest heavily in agriculture, right? Because their population is less and they are pretty automated. I mean their agriculture has been pretty mechanized. But India needs a lot of automation in agriculture, a lot of improvement in the, increase in the yield of agriculture. So a lot of IoT chips would be needed in India, and also healthcare, right? I mean, we need a lot of this all these extra machines or dialysis machines, right? There are huge number of very costly machines which are used in healthcare, which are totally imported from outside, and they need very costly chips, right? Those chips can be manufactured in India very well, right? So that's why the autonomy of India, or the self-reliance in semiconductor will come from, right? And even if India invested in very high-end, chips, right? Yes, we can export that, but I believe first India has to become self-reliant in semiconductors, right? So for that we have to produce the chips that we need or we consume in our country, right? So in nutshell, I think yes, the if I'm not wrong, initially they were thinking about 20 nanometer, but what I heard actually, I think the first fab might be 40 nanometer fab, which is around 20-year old, even little more than that, because I think I remember around 2004 and 5 we already had 45 nanometers. So 40 nanometer might be late 90s or early 2000s. So it's little more than 20-year old, and it's a pretty stable sort of technology with pretty high yield, and also pretty like the machines equipment should be quite cheap. Fine, I think we are all 10 minutes past three, and I believe we also started a little late, so I think we are bang on time. So thanks a lot all of you for joining, and I hope that you liked it. I didn't want to make it too technical. I just wanted to give you an idea about the semiconductor industry, some history, because I believe we should also know our what India did in the past and what India can do in the future, right? Because that's where we all come into the picture, right? Because you will be working for the next 3 4 decades in India, and so I thought some history is needed, and also we should feel proud about the Indian connection to semiconductor industry. Not many people know that the first patent to be filed on a semiconductor device is held by an Indian. So we should be all proud about that legacy, and also we should be also very convinced that we should do big in the next few decades, right? So as I told, right, from zero revenue to 110 billion in the next 5 6 years, it's a huge leap. But I believe we all have to work towards that. We all have to move with confidence, with resolve, right? So that's the reason I wanted to make it rather than technical. I thought I would share some facts and figures which will help you to understand where what the industry is and what you can do in this industry.
Yes, sir. So thank you so much for taking up this session and having such a concise presentation of what's happening right now and what's the past of semiconductors. Many of the students are first year, second year, so they might not
Oh,
be
okay,
even open to the sessions at all.
okay.
So even these questions are coming from juniors itself,
Oh,
our
wow.
batch.
I mean, that's amazing.